Hi there everyone. This is the first video in a series of videos to do with the numerical solution of equations. And you will have solved many equations over the years, whether they were linear equations, whereby doing the same operation to both sides you found the single unique solution to that equation, or perhaps there were quadratic equations, where either by factorizing or using the formula or completing the square you found the up to 2 solutions that might exist for that quadratic equation. You've done some work with trig equations, where you know that you have to specify a range of values for the given variable so that you can find some of the infinite solutions that exist if you were to consider all values of x or your variable available. And then you've done some work with cubics, and I'd like to start with a cubic. X cubed minus 7x minus 6 is equal to 0. So if you were to approach this and try to solve this particular cubic, you would begin, I hope, by using the factor theorem. And if you did that, you might find that 3 is a factor. So if you were to insert 3, you would get 0. And so your next line of working would look something like this. So if I multiply those two brackets out, I'll get back to x cubed minus 7x minus 6. You might have come up with the quadratic in the second bracket using algebraic long division, or you may have done it by inspection. So now we have to further break down that quadratic, and if we do that, we find that x minus 3 and the double bracket for x squared plus 3x plus 2 would be x plus 1, x plus 2. And so we have 3 solutions. X is equal to 3, x is equal to minus 1, and x is equal to minus 2. What does this look like graphically? Well, I know minus 1 is a solution, minus 2 is a solution, and 3 is a solution. And from my knowledge of the sketching of curves, I know that because I've got a positive x cubed in my relationship, that the curve is going to look something like this. So finding the solutions to x cubed minus 7x minus 6 equals 0 is the same as finding where the curve y equals x cubed minus 7x minus 6 crosses the x-axis. I should say also that where this graph crosses the y-axis will be minus 6, and we can read that directly from the equation y equals x cubed minus 7x minus 6. Now we're going to make a very subtle change to the equation that we first solved there. We're going to try a different cubic, but the change is very subtle. So it's now x cubed minus 7x minus 5 equals 0. Well, if I rewrite that, I can incorporate the original function x cubed minus 7x minus 6, and then I can add 1 to return to minus 5. And what we have there is the original function plus 1, and that's a vertical move. So we're translating the graph 1 unit vertically, and in green you'll see approximately what that might look like on our new graph. Well, now we have a problem, because it doesn't look as if any of the roots to the equation, which you'll remember are the points at which it crosses the x-axis, are at whole numbers. One of them seems to be a little lower than negative 2. Another a little higher than negative 1, and the last one a little lower than 3. This is just the kind of situation that requires a numerical method of solving the equation, because there are no direct algebraic routes, no techniques that we can apply that will take us automatically to find the solution of this equation. You could use some sophisticated graphing software to find the coordinates of the point where it crosses, or you may have a calculator that has an equation solver on it, but those solutions will actually have been found by using the numerical methods that we're going to be talking about in this sequence of videos. So for now, I'm going to take off the original graph, the x cubed minus 7x minus 6 graph that we originally started with, so that we can focus our attention on the graph that we're now looking at. In order for us to see what's going on here, I'm going to divide the graph up into areas, into regions, on either side of the routes that we're trying to find. Now remember that the graph that we have drawn is the graph y equals x cubed minus 7x minus 5. And what we're particularly interested in is what is happening to the left and to the right of each of those solutions that we're looking to find. And if we look at the first section on the left, we notice that y is negative. It's less than 0. But immediately on the other side of the route, y is greater than 0. And that holds true all the way up until the second solution, which is just above -1. And if I go to the other side of -1, there y again is less than 0. That again holds true until I come to the third of those solutions, near to 3, and to the right of that y is again greater than 0. And the first method that we're going to be looking at really is all about this idea that from one side of a solution to the other, there is a change of sign. So let's apply the change of sign method to the equation that we're trying to solve, x cubed minus 7x minus 5 equals 0. This is something that you can do using the table function on your calculator, or you could set it up on a spreadsheet. I've chosen to use the table function on my calculator, using the values of x from -3 to +3, and these are the results that I got. So if we look at that table of values for y, we can see that there is a change of sign between -3 and -2. There's another change of sign between -1 and 0, and a final change of sign between 2 and 3. And that's broadly what we were expecting to find. And we're able to say that there is a solution between -3 and -2, another between -1 and 0, and another between 2 and 3. In order to progress this further, I would need to reduce the gap between the values of x that I take. So rather than having a step of 1 unit, I would reduce it to 0.5, and then the table of values that I get would look like that. Well, with those values, I can see that there is a change of sign, first of all between -2.5 and -2. Another change of sign exists between -1 and -0.5. And the final change of sign takes place between 2.5 and 3. And so now I have reduced intervals for each solution. So I can now refine my statement of the intervals between which the solutions lie. So now, rather than having very, very long and extended tables. I'm just going to consider one of the solutions, the one between 2.5 and 3. And again, I'm going to reduce the steps still more. This time I'm going to reduce it to 0.1. So my table goes up from values of x from 2.5 up to 3, and the corresponding values of y there are shown. And that indicates that the change of sign is between 2.9 and 3, and so the solution lies between 2.9 and 3. So we're able to say that there is one solution that lies between 2.9 and 3. I think you can already begin to see that this is a rather blunt instrument for finding the solutions to any great degree of accuracy. However, the change of sign method does have one further use. When we think we know the solution to a desired degree of accuracy, and we want to check whether we're correct in making that statement. Looking at the values that we've got in our table, it's actually quite hard to decide whether 2.9 or 3.0 would be correct to give as the solution to one decimal place. It does look as though 2.9, its value is marginally closer, because minus 0.9 is nearer to 0 than 1, which is the value that we have for 3. So we're going to make the assumption that the solution is 2.9 correct to one decimal place. If that is the case, then there must be a change of sign between the lower bound for 2.9 and its upper bound, and that's what we're going to check next. What we're saying is that if 2.9 is one of the solutions that's correct to one decimal place, there will be a change of sign between 2.85, which is the lower bound, and 2.95, which is the upper bound. So we put those values into the calculator, and these are the results that we get out. And we see that, yes, there is a change of sign. For 2.85, I have a value of minus 1.8, and for 2.95, 0.0223. And since it's already positive at 2.95, that means any further or nearer to 3 that we get, it's still going to be positive. And so the change of sign occurs somewhere between the lower bound for 2.9 and its upper bound. And so we are able to say that one solution of our equation is 2.9, correct to one decimal place. So we've seen that the change of sign method is rather clunky and difficult to use to find answers to a high degree of accuracy, but it does have two functions which are very, very useful to us. First of all, we can very quickly establish an area, a region in which we believe a solution to exist. And then, having perhaps done some more work, and with a value that we believe to be correct, we can check its upper and lower bounds to determine whether that proposed solution is correct or not. Finally, we need to consider the possibility that this change of sign method might fail. And there are a number of cases where this can happen. Consider this graph. We can see that there's a vertical asymptote. And to one side of that asymptote, we have a y value that is negative when x is equal to a. On the other side of the asymptote, when x is equal to b, the y value is positive. And so, although there is a change of sign in the interval between a and b, because the graph doesn't actually cross the x-axis, there is no solution that exists within that interval. Similarly, if there is some other form of discontinuity, there are occasions where to one side you may have a negative y value, and to the other side a positive, which suggests a change of sign and therefore a potential solution, but that solution may not exist. Other cases of failure are possible too. For example, in this graph, we have an interval, and within that interval there is definitely a change of sign. We might be expecting just to find a single solution, but actually there are multiple solutions. So more than one solution may exist within an interval. And we can overcome this by looking at smaller intervals. Perhaps our initial intervals are too large. But then equally, we may not be expecting to find a solution within a particular interval when there are still multiple solutions that actually do exist. Again, possibly because we've chosen too broad an interval. And of course, if the curve is actually tangential to the x-axis, so that there is a definite root that exists, on either side of that, you're going to have either both positive or both negative values for y, and you may not be expecting to find a solution within that interval. That concludes our look at the change of sign method. You'll see that it crops up with the other methods that we look at in later videos too.